Hello everyone, welcome back for lecture 3 of my introduction to materials for engineers. Today we'll look once again at plastic deformation, focusing more on dislocations, slip systems and diffusion and how these processes influence other material properties. But first let's do a little recap on what we learnt so far regarding plastic deformation. Well, you'll recall that the yield stress is the stress at which plastic permanent deformation occurs. And this deformation occurs by the sliding of atomic planes over one another under the influence of shear stresses. Now, for these planes to slide like that, you need a sufficient shear stress to overcome the atomic forces. Now, if a comparison is made between the actual and predicted shear stresses needed, you find a rather significant discrepancy. Theory based upon atomic forces indicates that this shear stress should be around 1/13 of the shear modulus, so around 1 gigapascal for a typical metal. However, a typical yield stress in a simple system with no grain boundaries or impurities, it actually turns out to be more like 1 megapascal. So there really is quite a significant discrepancy there, of 3 orders of magnitude. Well, why? Well, that's what we're going to talk about today, because that's where dislocations come in. So today we're going to focus on dislocations. And that discrepancy that we have, that can be resolved if you consider that the atomic planes do not in fact slide across each other as rigid sheets, but rather slip occurs in a localized fashion, progressing across the sheet in steps. And these localized regions of slip are called dislocations. Okay? And should you choose to represent a dislocation graphically, here is one I made earlier. This one specifically is an edge dislocation in a cubic structure, which can be thought of in a way as an extra half plane of atoms. This extra plane of atoms distorts the lattice within the vicinity of the dislocation core, within a few interatomic spacings of the bottom row of the extra half plane shown in this figure in the center of the page here. Now, for different materials, dislocations will cause larger or smaller distortions to its surroundings. And these dislocations will slip or glide as shown in the schematic below that figure. So you can see with the caterpillar there, you get this gliding across the lattice, as you can see with the caterpillar as it crawls. Now, I've got to introduce a bit more sort of terminology here, so I'll explain that. A dislocation line vector and a Burgers vector. Okay. Now, dislocations are line defects. That is, as in the distortion of the lattice occurs along a line. Yeah. Which, let's take this edge dislocation that I've shown in this figure, is the bottom row of the extra half plane of atoms. Okay. So for an edge dislocation, it's the distortion of the lattice that occurs along a line, in this case the bottom row of the extra half plane of atoms. And this direction, the dislocation line vector, is an important characteristic of a dislocation, although it can change as the dislocation moves. But what about the magnitude of the displacement that's generated? Well, for that, we have a Burgers vector. So that's our next bit of materials vocabulary we need to understand. And the Burgers vector gives both magnitude and direction. And that can be obtained by tracing the path around the dislocation which closes. Should there be a closure failure in a perfect crystal, the magnitude and direction of this closure failure defines the Burgers vector. So, how do these dislocations move in a crystal? what governs the planes in which these dislocations glide? Well, this is where we need to talk about slip systems. Okay. So, with respect to sort of slip systems, for an edge dislocation, the Burgers vector is normal to the dislocation line vector. These two vectors basically define the slip plane. Yeah? The Burgers vector and the line vector. And the combination of the slip plane and the slip direction, which is defined by the Burgers vector, are often called the slip system. Typically, the most closely packed planes, i.e. where the atoms are closest together, that constitutes the normal slip system in a given crystal structure, which is what I've shown in the table here in the center of the page. Okay, so the Burgers vector of a particular dislocation has to lie in the slip plane on which it's gliding. And that's stated by the Weiss zone law that we covered previously. Further to that, the Burgers vector of a perfect dislocation must be a lattice vector given its passage leaves the crystal structure unaffected for a perfect dislocation. Now, I said before, not all dislocations are edge dislocations. There are also screw dislocations. And screw dislocations have their Burgers vector parallel to the line vector. And they're called screw dislocations because the helical displacement of the atoms that surrounds the core, as shown in the figure at the bottom of this page here, page 28, where I've identified with an arrow showing the direction of the dislocation line and the Burgers vector. And since the Burgers vector and the line vector are parallel, there's a family of potential slip planes. Okay? So during slip, the dislocation line moves normal to the applied shear stress, producing slip in the direction of stress. Now, despite the fact that, I've mentioned edge and screw dislocations, in fact, most dislocations are actually mixed, i.e. the line vector isn't parallel and it isn't perpendicular to the Burgers vector. Now, if you take a look at the figure at the bottom of this page here, page 29, that shows for an edge and screw dislocations the resulting slip. Dislocations move, they leave behind them a slipped part of the crystal. And this displacement is always the same for the slipped part relative to the unslipped part. Given that consistent displacement with the movements of a dislocation, for the crystal structure to be left unaffected by the passage of a dislocation, the Burgers vector must be a lattice vector. And such dislocations are termed perfect dislocations. All right. So, how do we measure these dislocations? Well, I've mentioned previously something called the dislocation density. Well, let's look at what exactly I mean by dislocation density, because that's quite important. It's quite an important measure when looking at the mechanical properties of a material. Well, a material's dislocation density is a measure of the total dislocation line length per unit volume. As such, it has the units of per meter squared, okay, because it's a measure of the total dislocation line length per unit volume. So units are per meter squared. And we can make comparisons or very basic estimates of dislocation density using, even simple electron microscopy, as the dislocation density will also equivalently be the number of dislocations intersecting a unit area, with the dislocation density being related to the average spacing between those dislocations. And that's what you see in the equation here at the top of the page, where rho is the dislocation density and L is the average spacing. Now, typically, dislocation densities in metals will range between 10 to 10 meter per meter squared to 10 to the 16 per meter squared. So 10 to the 10 to 10 to the 16 per meter squared. That's equivalent to average spacings of 10 microns to 10 nanometers between the dislocations. And these dislocation densities, they'll greatly influence mechanical properties. The higher your dislocation density, the harder it is to plastically deform. So the material and the dislocations within them begin to interact with one another and restrict plastic deformation. So a higher dislocation density means a harder material, more resistant to plastic deformation. And it's these interactions with dislocations that cause barriers to their own motion. That we see similarly with dislocation precipitate interactions. Precipitates, much like other dislocations, they can be barriers to dislocation motion, which increases the yield stress, i.e. it increases the resistance to plastic deformation. And this is what the figure in the center of the page here, well, at the bottom of the page here, shows. And this is an aluminium copper alloy under different heat treatments. And each heat treatment causes different sizes of precipitates to grow. And these different sizes of precipitates will inhibit dislocations in their gliding to different extents. Should you produce large precipitates following, say, a long or higher temperature treatment, dislocations find it easier to bypass them because they bow around the precipitate. But if you have smaller precipitates following, for example, a lower temperature or reduced time treatment, dislocations actually cut through them rather than bowing. So too small and they're too easy to cut, too large and they're too easy to bow around. So the optimal size found in this graph to be around, for the heat treatment of around 150 degrees Celsius, the optimal size is at the point where there is greatest resistance to dislocation motion, where bowing and cutting are equally favourable or unfavourable. And we'll go into more detail on precipitates when we come to lecture 4. Okay. But before we go into precipitates, though, we've got to cover one other basic aspect of materials, and that's diffusion. I've mentioned diffusion quite a lot so far, and mostly in terms of the movement of atoms. And that's what diffusion means in this context, the atomic movement of atoms in a crystal across a network of atomic sites occurring generally as a result of thermodynamic driving forces, most often due to a concentration gradient. Now, there are several things we should cover first, really, on the basics of diffusion. First being random walk. If one considers an atom jumping from one position to another across a distance of lambda with a frequency, and when I say frequency I mean number of jumps per second, with a frequency of v, v is equal to the following equation shown on at the top of page 31. Now, for an n number of random jumps, the average distance, x, travelled away from the origin of that atom after a given time, which we'll call t, is given as follows. So x equals lambda root n. It's showing that the diffusion distance is proportional to the square root of t. Okay, which is quite important. Now, further to this, there are two types of solid state diffusion. You've got substitutional and interstitial, named after the sites that the atoms are moving to and from. Substitutional sites, interstitial sites. The figures below at the bottom of the page here show both. as you can see, interstitial diffusion occurs for interstitial atoms, such as carbon in steel, travelling between interstitial sites. Substitutional, such as iron in steel, requires the exchange of two atoms, or four atoms in a ring, or the movement of a single atom into a vacant site. And that vacant site is known as a vacancy. We'll talk about that later on. Because of the movement of an atom, because it requires distortion of the lattice, there's an energy barrier to that motion, to that movement. And that energy barrier is the activation energy. And that will be different for each type of diffusion shown here, these four different types. Now, if we look at Fick's first law of diffusion, that describes diffusion in a uniform concentration gradient. Let's take two planes of atoms adjacent to one another in the cubic crystal shown below. Now, across these two planes, left to right, is a concentration gradient of impurity atoms. And that's shown, the impurity atoms are shown in blue. Now, there will be an atomic flux of these impurity atoms in left to right and right to left. And the atomic flux is the number of atoms passing through a square meter per second. So we can write the following equations for left to right and right to left flux of said atoms. Okay, Rj with left to right and Rj with right to left. And the sum of those two directions will give us the net flux. And using Taylor expansion, we can find the following, that shown here, that the diffusion coefficient in units of meter squared per second multiplied by the concentration gradient, which is the number of atoms per unit volume, give us the net flux of said atoms. And that is Fick's first law of diffusion. This law is obeyed so long as the concentration gradient doesn't itself change as a function of time. So as long as it's independent of time. So let's look now at a macroscopic scale phenomenon of diffusion, specifically the Kuykendall effect. Now, there was a Kuykendall experiment, and in the Kuykendall experiment, we can evidence the vacancy mechanism of diffusion I mentioned previously. Take two different materials. One on the left, if you look at this graph, look at this figure. One on the left of atoms A, one on the right of atoms B. And they're joined together with inert markers at the interface between the two, forming a diffusion couple. And at high temperature, where reasonable macroscopic diffusion can occur, atoms A can be seen to actually move to the right faster than atoms B move to the left. And as such, there's a net flux of atoms to the right, whilst the inert markers remain stationary. But how does this show the role of vacancies in diffusion? Well, we can view this net flux of atoms from left to right as a flux of vacancies from right to left. As the equilibrium number of vacancies in A is low, but high in B, perhaps due to the lower melting point of B in comparison to A, well, that means that the vacancies tend to be created in B and will diffuse into A where they're destroyed. Okay? Now, what we see on a macro scale is that the inert markers appear to move to the left as the block remains stationary. As we see this movement of the markers, it confirms that diffusion occurs via vacancies. And that wasn't previously seen in other experiments. So it's an ideal experiment to present vacancy diffusion. Now, I mentioned that temperature in this experiment, I said hot and cold. Well, how does temperature influence diffusion rates. Here I said it had to be hot enough to produce sufficient macro scale diffusion. Well, if you look at page 35, this one, page 35, if an atom is a potential well of height g, yeah, and it vibrates with a frequency v0, the frequency with which it can make a successful jump into the adjacent position is given by the following equation. And combining this equation with the equation relating diffusion to interplanar spacing, which we went over earlier, we find the following relationship. And we can plot that Arrhenius plot showing diffusion as a function of temperature, which is the graph that I've presented here. And for that graph, which is natural log of diffusion versus 1 over the temperature, the gradient of the lines are enthalpy over the Boltzmann's constant, where the enthalpy term is the activation energy for diffusion. And that activation energy we can start to separate. And we can separate into two things. We can separate it into Qm, which is the enthalpy of migration due to lattice distortions, and Qf, the enthalpy of formation of vacancies in adjacent lattice sites. Yeah. So, given that, we can find the following equation for diffusion. Because since the formation of a vacant site isn't needed for interstitial diffusion, the second term isn't needed for interstitial diffusion, because you don't need that vacant site. And so the diffusivity of interstitials is far greater than for substitution atoms, because you don't need those vacant sites. But diffusion is similar for many metals at their melting points. For other materials, diffusion will depend on the bonding in the material. For example, diffusion for silicon is much lower because of its directional covalent bonding, and so there's much higher activation energy term for that. But now let's look at disruption of lattices and a bit more on vacancies. If you have a lattice that's locally disrupted, it'll have a more open structure. The activation energy for diffusion will be lower, and that will mean that diffusion is faster. And that's why on grain boundaries, around dislocations and vacancies, diffusion is faster, because you have that more open structure. The activation energy for diffusion is lower. And further to this, with more vacancies comes faster substitutional diffusion. Something we have to note is where these vacancies might go. And that's important for the main lecture course in nuclear materials. Okay, so certain microstructural features can act as sinks for vacancies, such as shown in the figure here for a dislocation acting as a sink for such a vacancy. As a vacancy diffuses towards it, these dislocations can also behave as vacancy sources. So you get the vacancy diffuses towards it and is absorbed, so it's a sink because it's trapped it, but then it can also emit the vacancy. It can be a vacancy source. So it spits out vacancies, and that's what you see on the figure on the right there, is when it behaves as a source. You can see it moving to the bottom right. Now, other sources of vacancies are plentiful. You can produce vacancies through rapid quenching of a material. Basically, that freezes in the high equilibrium number of vacancies present in a high temperature material. And as the temperature of that material is rapidly lowered, you basically freeze in those vacancies so they don't have time to be eliminated. Or you can increase vacancy number by mechanical deformation. That will also increase the number of vacancies. And really that's all you need to know for the main course. It's kind of a crash course on on dislocations really, and a little bit on vacancies. And that concludes our third lecture of Introduction to Material Science for Engineers. Next lecture, like I said, we're going to be looking at precipitates, and we'll focus on steels before moving on to the main lecture course. So I hope today was useful for you, and should you have any questions, once again, let me know, and I'll get back to you as soon as I can. All the best.